Okay, so I'll take over for this this next part of the lab. So the next part of the lab, we're going to talk about clustering and focus on two main kinds of clustering that are, likely the most popular clustering out. One is k-means clustering, and the other one, which is a sort of top-down clustering, and then hierarchical clustering, which is a bottom-up clustering, or divisive k-means versus agglomerative hierarchical. Okay, so now k-means is going to be fit using something again from scikit-learn. It's an unsupervised method. So because it's from scikit-learn, we're going to fit it using the fit method. But as we saw for principal components, when we actually fit k-means, we're not going to have a response. It's just going to be fit on the set of features. So here we generate some data. We'll plot the two we sort of made two natural classes in the data we'll see in a minute, and then we're going to fit k-means here with two clusters, so k equals 2, and we have this argument here n init, which is how many random starts to try and find an optimal clustering. And of course we use the same random state to reproduce our results, so we can each time we run the code we'll get the same answer. Okay, one key thing after you have run k-means is you want to see what points are assigned to what cluster, and that's the labels attribute. And okay, so that's an array here. We can see that as we had kind of constructed our data in two classes, and it sort of perfectly separates them. If we look at how this data is constructed, the first 25 are sort of in one class, the next 25 are another, and it's kind of perfectly found that for us. Okay, so let's make a plot of the k-means, plotting by label.
Nice choice of color there, Jonathan.
Yes.
Did you choose it?
Well, I must say, I think Python chose that for me. I'll leave it at that. But yes,
I think it looks better in the book.
Yes, on the monitor here, the yellow is quite hard to see. But so we didn't. So I'll just go back to the plot here. So we made a scatter plot of our data, and here the color argument, that's C, we colored by the label, and so this data was constructed to be very separate, and k-means does a great job here at separating them. But of course, in practice, we don't really know that our data is nicely separated, and we don't really know that 2 is the right amount. So we could try fitting, we might have to try fit k-means with other numbers of clusters. So let's just look at what happens when we fit 3 clusters to our data set instead of just the 2. Okay, so this plot is essentially the same as before, except the estimator here, the k-means estimator, has 3 clusters. So the colors, there are going to be 3 colors. One of them is still that yellow that was hard to see, but there's a yellow cluster over here, and then a green and a blue. And we can see here, it's hard to say that this doesn't seem as good as the one before. It seemed to have actually not even split. Sometimes you might see k-means would split a big cluster into 2, but it's kind of taken a bit off the edge of each. Sorry, it's taken a bit off the edge of each of these clusters. And this is a very toy data set. We can actually see it in 2 dimensions. It's rather hard to visualize what's going to happen in higher dimensions. Okay. So one of the arguments we talked about in the estimator is this n init argument. And it's recall that the way the k-means algorithm runs, as discussed in the lectures, is that there's an initial random assignment to clusters, and then the k-means algorithm tries to incrementally improve the within cluster sum of squares, that is to make it as small as possible by swapping points between clusters. However, every different initialization could result in a different solution, so we encourage you to run many, and that's what this n-init argument does. It runs 20, and it takes the one that has the best within cluster sum of squares. So here we'll just compare using 1 fit to 20 fit on our data. This data is pretty nicely separated, even with 3 clusters. It makes some difference. Using 20, we got roughly 5% improvement in within cluster sum of squares. Okay. So the other clustering type of clustering we're going to talk about is hierarchical clustering. And remember, the main difference between k-means and hierarchical clustering is, in hierarchical clustering, we start with small clusters and build them up as we go along the path, whereas k-means just directly tries to break into a fixed number of clusters. So in hierarchical clustering, one of the biggest choices you have to make is the so-called linkage. And remember, that's the rule that's used that decides how clusters are merged. The three main linkages are complete, single, and average. And I would say, rule of thumb, complete is kind of often has nicer clusters than the other two. We'll see an example later about single has this deficit that there's often no, in the dendrogram, which we'll see in a moment, there's not a nice place to break, whereas complete sometimes has a bit better place. Okay, well, in terms of the code, it is again a scikit-learn estimator, though it's an unsupervised estimator. So again, we fit it with just a set of features, X. Okay. So this has fit something that we can use to produce a dendrogram. And we'll see how to plot dendrogram a little bit later. So we'll also here, just for completeness, we'll use the other linkages and we'll plot their dendrograms as well. So the difference between these three methods is just the linkage. And let's compare the dendrogram. So to fit hierarchical clustering, we need some notion of distance. K-means actually needs data points themselves to fit, but hierarchical clustering can be fit just using a distance matrix. And it doesn't even really have to be formally a distance matrix. It's something like a distance matrix. And we're just showing you here how to fit such methods, such clusterings. Instead of fitting on X, we're going to fit on a distance matrix.
So this is a distance matrix between all pairs of observations in the data frame.
Yes, all rows in the data frame.
All rows.
Right. Often, like for principal component, we're looking at the variance, covariance of the features. That's one of the important things in principal components. Here, this is a distance matrix of the rows or the cases in the data set. So we had 50 observations, so we'll have a 50 by 50 distance matrix. And that's the only information needed to fit hierarchical clustering, so we can fit it with the distance matrix. So here, instead of being like a matrix that has cases and features, this is just cases by cases, so 50 by 50. Okay, let's plot our first dendrogram. So we're going to plot the dendrogram for the complete linkage. And so one of the things you'll often want to do is cut a dendrogram let's look at the picture, then I'll go back to what one of those arguments. So here's a picture of a dendrogram. And the points here, there are 50 individual points. We can see their labels. They're relatively small here, but nevertheless, these are the individual labels of the observations. And then each height here corresponds to some value in that D matrix where these two clusters were merged. And for average, so for complete and single, it is always a value in the D matrix. For average, it's going to be some function of the values in the D matrix. But roughly speaking, this is the distance at which the clusters were merged for all of the linkages. And so here we can see, we know this data has two classes, or two natural classes, because we constructed it that way. So if we were to cut this dendrogram here, that would break this into two clusters. And so any cut to the dendrogram is related to a cluster, and that's what these arguments up here are related to. So there's a threshold we can use to cut the plot of the dendrogram such that anything below will be broken into different colors. So here I've put the color at negative infinity, so there will be no cut, and everything above the threshold is black. And that's why we got this picture. We'll see some cuts in just a minute. Okay, so if I change the color threshold here, I'm going to change the threshold to 4.
Oh,
so that effectively has put a line here. And now we can see separate clusters. We can see, so cutting here cuts these 4 branches, and then there are different subtrees. Each subtree corresponds to a cluster. So you can specify a value to cut, like when you actually fit the clusterer, you can specify 4, or you can also specify a number of clusters, because there's I think there's n-1 clusters as you go up the tree, and so you can specify, and they're ordered by the heights these things occur at. So if you want to cut with 5 clusters, there is some value here you can cut and get 5 clusters, and you can use the estimator, the scikit-learn estimator, to get that as well. Okay, so the function that does this cut is this function called cut tree. Here we specified 4 clusters, and it's actually going to be equivalent to having cut at 4, but I also could have cut this at 4.1 or 3.9, and I would get the same number of clusters. So you can. There's also an argument here where you can put instead of a number of clusters, you could put an actual distance number. Or the height. Yeah, the height at 5.